Hola, bienvenidos a todos a otra sesión del coloquio del Instituto de Matemáticas. Hoy tenemos el gran placer de tener con nosotros a IIlyashenko de la Escuela Superior de Economía de Moscú, que nos va a hablar de la historia dramática de la teoría de formas normales en ecuaciones diferenciales. Thank you, Professor Yulij, for accepting the invitation. And go ahead.
Thank you. Newton discovered differential equations. Liouville understood that most part of differential equations cannot be solved explicitly. Poincaré suggested an idea that instead of solving the differential equations, you should make the coordinate changes. Change the coordinates as to admit simple differential equations instead of complicated given ones. I will mainly deal with two-dimensional differential equations. So let us start with an equation like this, and usually 0 will be a singular point, and we will be interested in the behavior of the differential equation near a singular point. The first question is, let linear part be non-degenerate. And suppose that lambda is the spectrum of A. When the coordinate change may be so done that the equation will become simply linear. So we have a picture like this. This is the neighborhood of 0 and our original vector field V here. We take a diffeomorphism, a coordinate change, H. We come to another neighborhood of 0, and we want that the resulting vector field V tilde would be much simpler than A. The relation between V and V tilde is the following. If x is this point, h of x is this point, then V tilde at h of x equals to the derivative of h applied to V at the point x. So this is an equation. V is given and V tilde is required to be simpler. And the first case is V tilde equal to AX, when we can linearize the equation. There are several ways to approach equation 1. On one hand, we started with an analytic diffeomorphism, H. And now it may be decomposed in the Taylor series. The coefficients of this Taylor series may be found recursively, usually. And the first level is the following. is it possible to find all the coefficients of the Taylor series H without taking care whether this series converges or not? So I give a definition. V and V tilde are formally or analytically equivalent. If equation 1 has a formal or analytic solution H. An obstacle, even for the formal equivalence, are so-called resonances. Resonances are relations on the eigenvalues of A like the following. Lambda j equal to lambda k, which is sum of lambda j kj, where k is a vector and it is like a vector exponent of a multidimensional Taylor series. That is, all the components are non-negative, and it corresponds to a nonlinear term. That is, the sum of the components is greater than 1. So this is the definition of a resonance. And the Poincaré theorem claims that a non-resonant vector field V, that is a vector field with a non-resonant linear part. A non-resonant vector field V is formally equivalent to its linear part. But formal equivalence does not at all imply analytic equivalence. So let me use I said that I will keep in dimension 2, so let me use the common material about the singular points in dimension 2. So singular points in dimension 2, once again, determinant of A non-equal to 0, and we have linear focus or a linear node or a linear saddle or a center. And For the linear case, the face portraits are like this. Or like this. For the saddle, it is like this. For the center, it is like this. And now we are interested in the case when the linear vector field is extended by nonlinear terms. So we consider a nonlinear vector field, analytic vector field.
The saddle is different.
The saddle was plotted like a node, whilst it is, thank you very much, Ernesto. So, do resonances occur in these cases? What is formal normal form? That is the simplest equation V tilde to which we formally can transform our equation. And what is analytic normal form? No resonances in the focus case. The formal normal form is linear, and the analytic normal form is always linear. This is a part of the Poincaré theorem, which was a starting point of the normal form theory. What about the node? If there are no resonances, then the normal form is again linear, formal normal form, and an analytic one is also. But if there are some, so if resonances are present, then this implies that the ratio of the eigenvalues is either integer or inverse to integer, and the formal normal form is polynomial. Analytic normal form is the same polynomial, and this polynomial normal form is integrable. So everything is okay with the nodal singular points. What about centers? The eigenvalues are purely imaginary and non-zero. And the resonances are always the sum of the eigenvalues equals to 0. Hence, the resonance is like this. So the formal normal form is integrable. But it is very far from the analytic normal form. I put here TBE to be explained. And it will be related with the second part of my talk. The saddle may also have no resonances, and this corresponds to the case when the ratio of the eigenvalues is irrational. Then the formal normal form is linear. but the theory of the analytic normal forms is very delicate. When the resonance is so there is no resonance, and there is a resonance, and it is the case when this ratio is rational. And this is a closely related theory to the case of centers, and I will explain it in the second part of the talk. So this is the program. I will not discuss the simple cases covered by the Poincaré theorem. And I will mainly concentrate on the case of the saddle. Poincaré himself did not overcome this difficult case. When the normal form is linear, the coefficients of the formal normal series that brings the equation to the formal normal form are sometimes expressed through the original coefficients as fractions with the denominators that tend to 0. And the first person who overcame this difficulty was Siegel in 1942, and he proved that if this ratio is not well approximated by rational numbers, then the normalizing series converge despite the existence of small denominators. And if the ratio is badly, If this ratio is badly approximated by rational numbers, so too closely approximated, then the normalizing series may diverge. All this may be, in fact, reduced to the one-dimensional theory, and I will now explain you the reduction. For the saddles, the Adamar-Perron theorem claims the existence of the analytic separatrices. So, Adamar-Perron theorem works in any dimension. I will discuss only dimension 2, and for the linear saddle, we have the eigenvectors of the linear part. They generate two straight lines. On one, the motion is to the singular point, on another from, and the orbits are like this. Adamar-Perron theorem says that in the nonlinear case, the invariant curves still exist, but they are not the straight lines, they rather are tangent to the separatrices of the linear part at 0. And they are analytic in case of the analytic equation. So if we have the real picture, it is like this. But we can consider a picture in the space C2. Then the analytic curves may be rectified. You can make an analytic change of coordinates that brings any of the separatrices, any of the invariant manifolds to the complex disk. I try to plot the four-dimensional picture in the C2. And when you make a circuit, you take a cross-section parallel. This is the z-axis, this is the w-axis. You take a cross-section gamma parallel to the z-axis and continue the solutions along a closed curve that makes one circuit around 0 and is located on the separatrix. In order to visualize the situation, you may consider the linear case. Then W will be expressed linear case. W is expressed as equals to C multiplied to Z over lambda. Lambda is lambda 2 over lambda 1. And when you make a circuit around 0, then the function W is multiplied. The coordinate on this line is W. If you take a point W here and make a circuit over this circle, then delta of W equals to nu times W. And nu is exponential of 2 pi lambda. In the case of the real saddle, lambda is real. The exponent is pure imaginary, and therefore, let me, delta of double, this is nu. This is nu. Nu equals to this thing. Lambda is real, and therefore the magnitude of nu is equal 1. Once again, in the non-resonant case, lambda is irrational. In the resonant case, lambda is rational. So in the non-resonant case, for lambda Diophantine that is badly the analytic normal form is linear. Now, analytic normal form of the germ delta. Let me, I am a little bit too fast. Let me say a few words that I have skipped. In the nonlinear case, the very same picture keeps, and the very same monodromy map. I did not use yet this term, monodromy map. This map delta is called monodromy map. It is analytic. It has the same linear part as in the linear case, but nonlinear terms as well. And it is the same as here. And if lambda is irrational, then this monodromy map is analytically equivalent to a linear one. Its analytic normal form, achieved by a coordinate change now in the one-dimensional axis, is linear. And lambda should be irrational and in a sense far from rationals, badly approximated by the rational numbers. And for the Diophantine number, the analytic normal form is linear, and for lambda Liouvillean, I do not write this on the blackboard, the analytic normal form is not linear. The normalizing series, the formal normalizing series, do diverge. So I do not write down the explicit condition for the Diophantine number. It was given in 1972 by Alexander Bruneau. He gave two conditions very close to each other and expressed through the continuous fraction that approximates lambda. One condition was necessary for the linearization. So if it is violated, then there exists the normalizing series that diverge, and sufficient one. It was sufficient for the convergence of normalizing series. And Jean-Christophe Yocose proved that the Bruneau sufficient condition is also necessary. So these are I write the name of Bruneau in this way. I will explain why. Then Yocose got his Fields Medal in '94, partly for this result. The student of your course, Peretz Marco, studied a lot what happens in the Liouvillean case. A student of Arnold Piartli made a contribution to the geometric study of this divergence. And I will not discuss more the Diophantine condition here. What about the name of Bruno? It is now written like this. The situation is that the ancestor of Bruno with this name was a French officer which came to Russia with Napoleon. He was captured, and his descendants had the Russian name Bruno, which is exactly the spelling of the French Bruno. But when this Bruno was transformed to the Western spelling, this letter was replaced by this, and now his name is everywhere written in this way, though his family name is Bruno, like this. So, what happens in the resonant case? In the resonant case, again, the monodromy map is the key part of the study of the analytic classification of complex saddles. I put the chalks on the right place, okay. So, it appears that the monodromy map in the nonlinear case brings all the information about the analytic class of the saddle. This is quite a non-trivial result. It belongs to Martinet and Ramis. Together with Sergei Voronin, we also had it but did not publish. Martinet and Ramis published it first. So I will discuss the monodromy maps only. Now, the first question is to find a formal normal form to the monodromy map in the resonant case. So we have a map nu of W equals to nu W plus and so on, and I will write it again. And nu is exponent of 2pi lambda, lambda is rational, then nu times nu power sum n equals to 1. And this is the resonant case for the one-dimensional map. Let us consider the simplest version. Nu equals to 1 itself. And what I will say will be about the most simple class of maps, analytic classification of the most simple class of maps, that is I replace delta by F, W by Z, F brings Z to Z. Now some simplifications come. What one wants to write down is Z square with a coefficient. This coefficient may be 0, and I suppose that this is not the fact. If it is not 0, then by a linear change of coordinates in the z-axis, one can make it equal to 1. So this form is, in a sense, a generic case of a next nonlinear term in the decomposition. Now, here came a cubic term. And for simplicity, now this is not a generic case, but just a simple case. I suppose that it is 1 also. The formal theory says that F is formally equivalent just to the sum of the first 3 terms. But this is not the best formal normal form, and I will show now why. Let us consider an elementary example. Consider a differential equation in the one-dimensional complex plane like this. The phase curves of this equation are very nice. On the real line, it is like this, nothing interesting. But in the complex line, it is a little bit tricky. Probably I will write this map, T. It is a so-called rectifying map. This map brings the differential equation like this. Everybody may easily check it. 2t dot equals 1. So the phase curves here are just the horizontal lines. And if you make back the transformation z equals minus 1 over t, then these horizontal lines will come to the circles tangent to the real axis. So this is an actual phase portrait of this differential equation. Now, the example is not this differential equation, but time 1 phase flow transformation z comes to the time 1 phase flow transformation of this vector field. This is phase flow transformation time 1 of the vector field z squared. And it is equal to z over 1 minus z. In this coordinate, it is just the shift by 1. And this coordinate change brings it to this transformation. If you will decompose this transformation into the Taylor series, you will get z plus z squared plus z cubed plus and so on. So this transformation, if you believe this, is formally equivalent to this. But it is a much better representative of the formal equivalence class. So this is what I will call F0. And the theorem is that the same statement F0 is a formal normal form for F. Now I come to the time when me and my students Sergei Voronin were young and worked in 70s over this problem. We were inspired by Arnold, who was interested in this problem. And I should confess that all of us were ignorant and did not know a lot of previous work already done with respect to this class of maps. We just started to study it for new and found that F0 is a formal normal form, and for a long time tried to prove that the formal normalizing series do converge. Though the mathematical community already knew that this is not at all the fact in many particular cases. Much later, it appeared that George David Birkhoff, with his universal interest to all the problems in the differential equations, already studied this equation and made the following steps. Now I tell you about what Birkhoff have done. Without knowledge about the Birkhoff work, I suggested the term Ekal-Voronin moduli to what I will describe now. Some people tell that it is more valid to say Birkhoff Ekal-Voronin moduli. So the title of this subsection is in written text, they are Ekal-Voronin moduli, so I write Birkhoff in brackets. Jean Ekal studied the same class of maps with quite different analytic rather than geometric methods, and I do not describe what he have done. The only thing is that he found similar results in a different way. This is the reason why we call this moduli Ekal-Voronin moduli. What in fact was known before? First of all, Arseny Shcherbakov and in parallel Camacho-Sad found that F and F0 are topologically equivalent. So if you have an arbitrary nonlinear map of the class that we discuss, then the picture will be topologically the same for any map of our class as for the map F0. So I reproduce the picture for F0 again. And this is, in fact, a picture for F as well. There is a distorted line and distorted circles. I do not show distortion, or better to say, when I plot the circle on the blackboard, they are very well distorted. So no homeomorphism is needed. So the result is the following, and this result is due to Fatou in 1920, but Frank Loret found that Law found this result even in the 19th century, something like this. So the result is the following. In a sector S1 that I have plotted now, the map F is analytically equivalent to F0. You can consider another sector, and in order not to make a mess on this picture, I just plot it separately, but in fact it is located here. So in the sector S1, all the orbits quit the sector and enter 0 in the negative time. In the sector S2, all the orbits enter 0 in the positive time and quit the sector in the negative time. I plot the continuous orbits, but in fact, when I iterate the map F, the points are jumping over these orbits absolutely as they do for the map F0, which is a time one phase flow transformation for z squared. So the statement that they found is the following. Let me make a step back. A dream was that there was an analytic map in the whole neighborhood of 0 that conjugates F and F0. And this dream failed. But something of this dream remains valid. Namely, F and F0 are analytically conjugated not in the full neighborhood of 0, but in two sectors, S1 and S0. H1 conjugates, makes the conjugacy in the sector S1, H2 in the sector S2. And the asymptotic series for H1 and H2 at 0 is exactly the formal Taylor series, the formal series that conjugates F and F0. So there is no analytic function for which this divergent series is a Taylor series. But there are two functions for which it is asymptotic and for which it is asymptotic to actual analytic maps. And the intersection of these two sectors, I will now plot the sector S2 here. In the intersection, the transition map is well defined. We take the map F as H2 to the negative 1 times H1. So it is mapped in the H2 of the intersection of S1 and S2. And this is a key map. First, it commutes with the normalized map. And second, in some appropriate coordinate in the H2 of the intersection, you see the intersection has two components. So in appropriate coordinates, the intersection also has two components. And in appropriate coordinate t, which is close to -1 over z. In an appropriate coordinate t, phi of t equals 2. First of all, it is defined in two domains, and they are upper and lower half planes in t. For plus, we have here the Fourier series in t for k greater than 0, and this is for phi plus, and for phi minus, we have the same Taylor series, the same form of the Fourier series. And these are the moduli, the Birgov-Ekal-Voronin moduli of the map. So after this complicated procedure, we found an analytic function which characterizes the map. And this was a great mystery. What functions are actually found in this way? Probably, as they come from one and the same source, f, they are just the identity functions. Birgov asked this question and found no answer to it. And I will say a few words about the realization of this moduli. This will be the end of my talk. So, why every modulus like this may be in fact realized? The answer is the following. For the explanation, I will go a slightly different way than it is done in fact. This slightly different way is the following. Let us describe this transition function in the original z coordinate. So we have, in fact, two sectors now with the map F0 in them. And we have the gluing map, the transition function phi, from one sector to another. And on one hand, it seems to be very far from the neighborhood of 0 and the map F in it. On the other hand, we make the following bold thing. We glue the two sectors with the help of this transition map. Well, we get an abstract Riemann surface, that is homeomorphic to a punctured disk. As well, it is homeomorphic to an annulus. As well, it is homeomorphic to C star, the punctured complex line. And as F0 commutes with F, this gluing up does not break the map. So taking F0 in one copy and taking F0 in another copy will just give me the same map of this Riemann surface. So the map F on it acts. Now, the uniformization theory says that this Riemann surface may be bijectively and biholomorphically mapped to one of the three objects, punctured disk, annulus, and C star. And for those who heard my lectures, I may say that there is not only no conformal map of one of the models onto the other, but even no quasi-conformal map on one of the model onto the other. And it is not difficult to build by hands a quasi-conformal map, say G, of this map to the punctured disk. And if there is a quasi-conform of this Riemann surface, to the punctured disk, and if there is a quasi-conformal map, then there is a conformal map. And if there is a conformal map, now we get a classical punctured disk in the complex line and a holomorphic map on it. 0 is punctured, but the removable singularity theorem allows us to extend the map into 0. So we got a disk with a holomorphic map on it, and it was produced from all this long construction. So if you repeat back this long construction for this disk and the map on it, I still call it F tilde, it is in fact our original map F, and this is the end of the story. So I want to say that this theory, after the one-dimensional theory, it was developed in parallel. A similar approach was developed by Malgrange. The analytic classification of analytic saddles and centers was produced by Martinet and Ramis, and since then there was a lot of work in this direction, but I wanted just to tell you about these first fundamental steps, which are not very recent, but are necessary to understand the further development. Thank you.
¿Hay preguntas?
In your title it is written that this is a dramatic story. Why is it dramatic?
Probably all our expectations and the Birgov's puzzling, from my point of view, these are dramatic episodes. You can share or not share my view.
¿Alguna otra pregunta?
And the continuation may be also dramatic. The continuation may be also dramatic.
I will not say so. Probably it was not so puzzling, more natural. But still, when the problems were posed, the results were not evident. It was a difficult thing to do it. In particular, Jean-Pierre Ramis told me that it is known that together with Martinet, Jean-Pierre Ramis gave an analytic classification of so-called saddle nodes of two-dimensional vector fields. These are vector fields with 1, 0 and 1, non-zero eigenvalue, and Ramis told me that they are proud to do that, though Malgrange failed to do that.
I want to ask you, you mentioned that for these saddles, the monodromy map has all the information. Does that mean that the monodromy maps are conjugate if and only if the vector fields are analytically conjugate?
Yes, are orbitally analytically conjugate. Yes,
okay.
yes, exactly so. Yes. This was a theorem that we proved with Yelizarov, and Martinet Ramis proved independently.
¿Hay alguna otra pregunta? Bueno, si no hay más preguntas, démosle las gracias al profesor IIlyashenko de nuevo.
Thank you.